$20 minutes? 20 minutes? Okay, we'll do this. We'll make this quick, 20 minutes. GM, everyone. Thank you all very much for having me. Wait, no, I think we gotta go back a slide. Cool. So, yeah, if you don't mind, would love to start with an exercise. And in this exercise, what I'd like you to do is cast yourself into the future. We're here in the Museum of Future, so let's pretend a bit. 70 years down the line, you're walking down the beach. There's a bunch of Optimus robots that are coming and delivering you a bunch of pills. You're taking the pills and you feel amazing. You actually feel so amazing that you actually feel exactly like how you feel right now. How cool would that be? Well, this process is called backcasting, is what the longevity field calls it. And it's basically imagining a future so clearly that you can actually work toward it today. And I think what we have done, which is super important to consider, is that the future and the current medical system don't intersect. Basically, the structure of the existing medical system does not set us up for the future that we just described. And so this is why we founded Pump Science, because the system isn't taking care of us. It was never designed to. And so we basically need to create a game that gamifies health and that enables us to drive toward this future that we just imagined. And so we created the infinite game, which we call Pump Science. Cool. So in order to make this vision a reality, where we have AI basically predicting what will help us live longer, we're taking that and it's doing its job and just constantly iterating. Basically, we need to train AI to do that, right? Like that is the mission. And so there's a huge problem. And this problem is there's no training data. So I think, Peter went and talked a little bit about that there are databases where this information exists, but ultimately there isn't a closed loop feedback system whereby we can make predictions, test those predictions, and see whether they work and iterate. That training data set just doesn't exist. And so if we want to create a scalable mechanism to generate this training data, we need to create an entirely new system that tests a bunch of different drugs and just sees whether or not they make animals live longer. And so I think what a lot of people actually discount is that the scientific apparatus doesn't always solve the most important questions. So the question of what should we be taking every single day that will help us live longer might be an important question, but it doesn't mean that the scientific apparatus has solved it, right? So here are just some numbers to put what I'm saying into reality. So you've got 325,000 known natural products. These are just basically compounds that exist in nature. There are 36 billion synthetically accessible compounds. So this is with some medicinal chemistry, you could basically create this chemical. So with these numbers, just guess in your head how many you think have been tested on animals to see whether or not they make them live longer. The answer is probably much smaller than what you thought. It's less than 2,000. It's actually closer to 1,000. There's 36 billion compounds that we could test, and just over 1,000 have actually been tested. So our whole idea is we got to pump these numbers, right? And the secrets to longevity might be right on our fingertips. We just have not gone out and tested them. So let's go find them and build an actual training data set that, at the same time. So what we're building at Pump Science, in partnership with our scientific partners and our community, will become the largest open database for lifespan data, unbiased, cross-species, and AI-ready. Our experimental protocol starts with C. elegans, followed by flies, mice, and human testing. So the question is, and we get this question a lot, why not just immediately go to humans? Well, if you look at the cost, both in capital and time, it's extremely difficult to test a compound to see whether it extends life in humans. Even testing in mice is pretty expensive. Those 325,000 naturally occurring compounds, if you wanted to test every single one in a mouse, it would cost you $325 billion. So likely you have to test them on cheaper and smaller animals. And so what you actually realize is that this is an optimization game around getting the most longevity signal per cost time. In short, we're dying right now, and if we want to escape death, then we have to figure out how do we increase the amount of signal that we can send to AI so that it can basically start to make these predictions ASAP. So our team does a lot of research online, asking people that are in the longevity, health, and wellness community about supplements, and all of them basically only look at human tests. If we ever try and show them human studies, they just come to us and say well, there's no human evidence, so I'm discounting everything you're saying. I think the problem is if you're always waiting for that human longevity study, you may die waiting for it and never get it. So the question is, why do we start with C. elegans? I think Peter did a great job basically saying, look, humans are not worms, and totally agree with that, and the mechanisms by which we age are fairly different. We are only 35% similar to C. elegans, but at the same time, the speed and cost advantages of testing on C. elegans are so great that it potentially makes up for the information that's lost between a worm and a human, right? So a helpful analogy here is the C. elegans is basically like the graphics processing unit of longevity in biology. It is the fastest, cheapest way to send information to AI that will basically help us generate the signal that we need for necessary predictions. So look, C. elegans has a lot of limitations, certainly not discounting that, but I think the most important piece here is that it is the cheapest, fastest way to get information on what fundamentally changes the aging phenotype. So if you believe in this idea and you say, okay, C. elegans is the right model to test in, then where do you actually go run these tests? And the answer seems to be Aura Biomedical. They are running C. elegans testing at high throughput in an extremely cost and time efficient way. And they've automated a vast majority of the process. So they have liquid handling, they have computer vision, they have automated imaging, and they are basically not only helping us generate this AI-enabled data set, but they are embedding AI into the actual experimentation to make it extremely cheap and increase the reproducibility. So I can't describe to you the feeling of going in there and seeing these racks of worms on these different plates, and just thinking to myself, wow, they're actually creating the NVIDIA for biology. So we're super thankful for our collaboration with them, and they're certainly the foundation of our protocol. So after worms, assuming compounds don't harm the worms and potentially can extend their life, they move on to flies. And so flies live about 2 to 3x longer than worms, and they cost about an order of magnitude more. But the cool part about the flies is that we are actually monitoring their movement in real time. So not only are we waiting for them to die and get their lifespan data, but we can actually track their movement and get measures of health span. And so one thing that we're really trying to do is gamify the whole process of funding research. And so what we've done is basically hooked up the fly races that we're using. Where basically we slam the tube of flies to the floor, the flies run up to the ceiling, and we track their speed, and we're able to basically make a game out of this, where you can predict whether the control or the flies receiving drugs will run faster. And we have just basically a whole user experience around this that we're launching this week. And so not only is this a scientifically valid and valuable experiment, but it can also be entertaining with the right user experience around it. So one criticism we often get is how are you going to get non-scientists into science? And the answer may be because we can make it intrinsically fun, and that is a huge part of our goal. Cool, so rather than testing mice for longevity, which is obviously really expensive and time-consuming and potentially not fitting in with the attention spans of many of the crypto traders, we've elected to use mouse rotarod testing. And so what this is it's basically a test to see the endurance of mice. So we give different compounds to the mice and see, do the compounds help them stay on the rod for longer? It's super correlated with lifespan, so the older the mouse is, obviously the worse it performs. And so what we're trying to see is, can we actually improve their endurance as a surrogate for whether or not they will live longer? And then for human testing, which we haven't done yet, we haven't done a single human test, but we're very much looking forward to it, we'll likely use VO2 max. VO2 max is basically a metric for cardiorespiratory fitness, and it's a great correlate with human longevity. So, there are lots of aging biomarkers out there. All of them seem super interesting, but VO2 max predicts all-cause mortality extremely well, so that's why we've gone with it as a biomarker in the short term. Cool, so let's talk results. I think lots of people look at us as a project and they say okay, this is, kind of a joke, or there's too many memes for me to take this seriously. So we want to take a second here and show you what we've actually produced scientifically. So we've run 5 C. elegans experiments to date. And the top performer we found in terms of extending the lifespan of the worms is rifampicin, which extended the life of worms by 32%. Coming in second place thus far is EGCG and sulforaphane. EGCG comes from green tea extract. Sulforaphane comes from cruciferous vegetables like broccoli. And then in third right now is artemisinin, which increases the lifespan of worms by 20%. It comes from a worm, I forget the name of the plant. Anyway, it is currently used as a malarial treatment. Cool, so that's the worms. Now, going to the flies, we've only completed 2 fly experiments on rifampicin and urolithin A. It tells a pretty interesting and consistent story, which is that urolithin A seems to extend the life of flies and also increase their locomotor activity, while rifampicin decreases both. And so just looking at the more granular data, the result seems to be significant. So on the right side, we are tracking speed. Basically, the flies that take urolithin A move faster than the flies that are taking control, and rifampicin seems to actually slow their speed. So this is the coolest part about doing computer vision tracking, is that we can actually measure this in a completely automated way. Moving on to the mice. So we tested the 2 compounds, rifampicin and urolithin A, on, we started off with 9 mice, and basically we wanted to see, do the compounds increase their latency. So what you want to see here and in crypto is chart up and to the right. And what you'll see is for the control mice, they improved their latency by 61%, the rifampicin mice improved by 60%, and the urolithin A mice unfortunately dropped, thanks to our friend Kevin Durant, who dropped off on the very last data point, unfortunately. So I think, honestly, the biggest lesson from the mice trials thus far that we've received is that, yes, we're trying to be super cost and time efficient, but it comes at a cost, which is statistical power. And so, we had a few mice die, and now we're left with 2 mice, and you have 1 slip up, and then there goes your whole experiment. And so, honestly, this has been the biggest a much bigger lesson in experimental design than in understanding what the effects of the compounds actually do. So we may have flown a little bit too close to the sun here, trying to be efficient. One super interesting thing of monitoring the animals in real time is, so 2 of the mice died, and so we actually went and investigated what actually happened. And so basically, the mouse on the left, his name is Elon Musk. He got a skin rash, a topical dermatitis, and the other mouse basically licked it until it got infected, and unfortunately had to be euthanized. Cool. So just basically summarizing all of the results, our top performer right now in worms is rifampicin, our top performer right now in flies is urolithin A, and we still do not have a crowned king of the pill in mice. And so, yeah, basically we have a ton more experiments going. I think we've got 38 worm experiments in progress. I'm not sure if you guys can read that, but yeah, basically 50 experiments that are ongoing at the moment, which is super cool, and our goal is to generate this massive data set and increase the throughput as much as we possibly can. And really the end goal of the protocol is to create a leaderboard, right? So basically, which compounds extend life with the greatest evidence, basically. And so right now, our leading contender is urolithin A. And so what you basically do is you look at how it performed across all the animals, you weight it by how similar those animals are to humans, and now you can basically rank order which compounds should potentially go into an end product. And so, as we look forward to creating these kind of like multi-ingredient products that are made of natural compounds, this is how we'll decide whether to prioritize them. And so just have completely transparent data that is resulting in basically a longevity stack that is completely evidence-driven. Cool. So one super exciting announcement is that we are publishing a preprint in partnership with Research Hub this week. Basically, all of the findings that we've had with Riff and Neuro, we're going to be publishing with them. Super exciting, and there will be peer review bounties associated with that. So if you are interested in peer reviewing the data, we're putting it all out there on Research Hub, and you can go criticize it till you're blue in the face. Yeah, science. Cool. So look, we've talked to a lot of longevity scientists about this entire protocol, and there are certainly some like points of friction where they disagree with some of the design decisions, but ultimately it's fairly consensus what we're doing. It's not super crazy. But the question is, okay, how do you accelerate the funding around all of this, right? Like that's really what's novel. And so really, I think what makes us different and potentially transformative is by putting the pump in pump science. We got to go? Okay. Thank you.